Okay, so all this work we've done with ratios and proportions has led us to similar polygons. So lesson 6.3 is going to involve using similar polygons. And what we did in class today, you should have realized by measuring those two photos of the sailboats, where one was an enlargement, that the angles are all the same measure, but the lengths change. In fact, they're proportional. So let's get that in our notes. That similar figures, two important things about similar figures. The first is that all corresponding angles are congruent. And the second is that all corresponding sides are proportional. So like congruent figures with the angles, not like congruent figures with the sides. And so for example, what we have here is triangle ABC is similar to triangle DEF, and we can write it this way. Triangle ABC, and this squiggle, the squiggle mark, is the is similar to mark, just like is equal to, is congruent to. So we read this triangle ABC is similar to triangle DEF. Now when you're writing these, just like you want to be careful with congruent triangles, in that A corresponds with D, so they had better be in the same spot. B corresponds with E, and they had better be in the same spot. So just like congruent triangles or any polygons, the corresponding vertices have to be in the same position. So what we know here, the first part is that the corresponding angles are congruent. So we know as soon as they tell me that triangle ABC is similar to triangle DEF, I automatically know angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F. You can mark those if you want. And that's the easy part to mark. The more difficult is to talk about how the corresponding side lengths are similar. So if so we know that if we're going to look at segment AB to segment DE, that's going to be the same as AC to DF and BC to EF. In fact, we could put in some numbers. Let's say that this is 2, 4, and 5 in terms of inches, just making this up. And to keep it easy, if I knew that this was 4 inches, you can see that AB to DE would be 4 to 2 or 2 to 1. And so that means that we want all of these sides to be in 2 to 1 as well. As the proportional would mean the ratios are equal. And so to get from here to here, you double it. So we're going to double this one, and we're going to double this one. Of course, a ratio of 2 to 1 is pretty easy. They get more complicated, but as we're learning, that's maybe a good place to start. Scale factor. I almost used the term scale factor just then and realized we haven't talked about it yet. Scale factor is the ratio of the side lengths of the corresponding sides of similar figures. So besides just saying the ratio, in this case was 2 to 1, you could say the scale factor is 2 to 1. And I have an example here. In this case, they give you all numbers. So all the numbers are here for triangle TRS and triangle ZXY. We probably should go ahead and say triangle TRS is similar to triangle ZXY. That's a Z. There we go. And so then you know that you can take any corresponding sides to get the scale factor or the ratio. So I've chosen to do TR to ZX, which is 25 to 15, so the scale factor is 5 to 3. Now if you wanted to, you could prove that these were similar by doing the same thing here, saying 30 to 18, which is 5 to 3, 20 to 12, which is 5 to 3. So because I was told that they are similar figures, I knew that they would all have the same ratio or the same scale factor. So scale factor is just a new vocabulary word for us. Here's an example where they don't give you all the sides. So we have triangle EDF is similar to triangle, let's write that in since that should be there. Triangle EDF is similar to triangle NMP being careful to name them correctly. And we want to find x. So they give you all of the side lengths with the exception of EF. Now, there's two different ways to go about doing this. You could think of it as long side to short side. And I think for the moment I'm going to ignore the 12 and the 16 because they didn't need to give that to you. You could certainly make proportions with the 12 and the 16, but I'm going to stick with these four numbers here. So definitely, first of all, we definitely want to make sure that x is involved, right? So we don't want to, I could make up proportions. In fact, Miss Siski explained that there are 8 proportions if I don't worry about adding the denominator. There are 8 different proportions, but that's not going to help me get x. At least directly. So what we want to do is you can either go long side to short side. So x to 9 is equal to long side to short side. And that's how I started this. Sorry. So I started with x is to 9 as 20 is to 12. And of course, using cross products or means extremes, you get 12x equals 180 and x equals 15. And since they just the directions were find x is all we need to do. Now, you can take this and you can write 8 different proportions. So you have to be careful when you're correcting your homework. You might have something different here, come up with the same answer, but your proportion might be true. I could take those same things and go short side to long side equals short side to long side. The other thing you can do is do long side of the little triangle to the long side of the big triangle. And that's what I've done here. I've gone x is to 20 as 9 is to 12. X is to 20 as 9 is to 12. You'll see that I get the same equation and the same answer. And I could have gone 20 is to x as 12 is to 9. The important part is consistency. So if you're going to go from big triangle to little triangle, you've got to go big triangle to little triangle. If you're going to go long side to short side, you've got to go long side to short side. The only way that you're going to get it wrong is if you mix it up. And let's say you go long side to short side and then short side to long side, then you're going to get the wrong answer. So you really have to be consistent. It doesn't matter if you stick to one figure for the first ratio and go to the second figure, which is what I've done here, or if you want to, again, go big triangle, little triangle, big triangle, little triangle. Or in this case, little triangle to big triangle, little triangle, big triangle. And of course, we could do all this instead of using the 9 and the 12, I could have used the 12 and the 16. So you only need to set up, even though there are 8 correct proportions, you only need to set up one proportion and follow it through. Okay? Perimeters. Because of the fact that perimeters are length, whatever the scale factor is for any two similar figures, the perimeters have the same scale factor. So in terms of getting this down, perimeters of similar figures, the ratio of the perimeters is equal to the ratio of the corresponding side lengths. Or, in other words, you have the same scale factor for perimeters. That's not true for area, and we can explore that. Perimeters are length, sides are length, so that's why they have the same scale factor. Area is not length, so we want to be careful of that. So when we're looking at this example, our last example, we have two quadrilaterals that are similar. Again, I seem to keep forgetting to do that. I apologize. So I'm going to say A, B, C, D is similar, A, B, C, D, to E, F, G, H. Okay? And so those two quadrilaterals are similar. And you'll notice that I have 4 side lengths here, 2 feet, 3 feet, 5 feet, and 6 feet. I only have 1 here. And the directions that I have here is to find the length of segment FG, which I've replaced with an X, and the perimeter of the larger quadrilateral. So the first thing I did was I set up 2 is to 3 as 3 is to X. I could have gone 2 is to 3 as 3 is to X because those happen to be the same thing. It looks like the exact same proportion. There are 8 different correct proportions for this. So we're going to finish 2x equals 9, and we end up with 9 halves, which normally, particularly if we have variables in our answer, I'd prefer the improper fraction. But because we're talking about a length, if I say how tall is that student, 4.5 feet makes more sense than 9 halves of a foot. 9/2 feet. So we have 4.5 feet for the measure of segment FG. Then what we want to do is find the perimeter. To get the perimeter of the large figure, let's start with the perimeter of the smaller one. 2 plus 3 plus 5 plus 6. If I did it right, is 16 feet. And then the scale factor, because this, we only have the only two sides that we have to compare are these short sides here. So the scale factor is 2 to 3. I don't have to simplify that. Remember, all your ratios should always be in simplest form. It's already in simplest form. And so I have little to big. So if we know that the perimeter is 16, I'm going to go little to big. So I did little to big, little to big. And I called the perimeter of my big quadrilateral y. And so I finished at 2y equals 48, y equals 24 feet. So the perimeter of this is 24 feet. Hope that helps.